Okay, so possible applications. Well, one of them is very obvious. Just the presence or absence of a conducting phase at the nanoscale could be used, in principle, to store information. And so we've done some experiments so far. Basically, in this case, instead of writing with a continuous voltage, we can pulse a voltage of various durations and separate them by distances d. And what we expect to see is an insulator to metal transition when the diameter of these disks becomes comparable to their separation. It's a way of trying to quantify the width of the diameter here. And what we saw is that, of course, if this pulse duration is large, then the islands themselves are large, maybe 30 nanometers, but they can be basically go down to the order of about 1 nanometer, it looks like. So this is very interesting, of course, for the point of view of being able to store lots of information on your pinky. So just for reference, right, that's about 10 terabytes on somebody's pinky. So another thing that's kind of interesting, also possible undergraduate lab. This is not something you need to do at very low temperatures, at ultra-high vacuum, and so forth. This can really be done on a cheapo AFM. So basically, it's exploring quantum mechanics at room temperature. So what we did was we start with a wire, and then what we're doing is we're basically slowly erasing a middle region of the wire. And so you can think of it as basically having a barrier in the wire that's getting taller and taller. And so what you expect to happen is basically what we observe is that there are 3 distinct phases. So so we actually apply minus 50 millivolts, a very small negative voltage. We're just, let's say, removing 1 hydrogen ion at a time, slowly raising that barrier. What we see is that initially not much happens. In that initial phase, you're basically still in a metallic phase, but then you get to a point where each time you move over it, you get an exponential or geometric reduction in the conductance. So this is basically due to thermal hopping. So at that point, you have thermal activation over barrier, and then if you follow that line, it would go all the way down to here, but we don't see that's in disagreement with our classical theory, but in fact we know that the system should behave quantum mechanically. The electrons should be able to tunnel through the barrier, and that's basically what they do. And the red curve is basically a qualitative agreement with a very simple single electron model, just showing this type of WKB approximation, square root of V minus E in the exponential. V is the height of this, which is proportional to how many times we have cut this wire. Okay, so that's what we see. Now, a few other things that we've done. If we take a wire, we cut it, and we shine light, then the light can actually act as it can be used to temporarily close the circuit. So it's basically a photoconductive switch. And what's interesting about this particular one, is that the area of sensitivity is very small. It's basically about 10 nanometers on a side. So it's at the molecular scale. It may be possible to use this to analyze single molecules and to do spectroscopy. Another thing that we're working with this is instead of using continuous wave light, we use very short pulses of light to create a terahertz radiation at the molecular scale, which might be useful for that terahertz spectroscopy. So kind of like when you go through the detectors, not the X-ray backscattering, but the terahertz ones at the airport, this would be for molecules. Okay, so transistor. Right, it's the most important invention of the 20th century. We don't know what the most important is for the 21st, but it's definitely the transistor. More transistors than any other human-made object on the planet. Right? So it was a natural target for us to try to make a 3-terminal device that was analogous to what could be done with silicon. So we already had the name worked out. We had the acronym and everything. We just had to do the experiment. But let me just point out that creating transistors from silicon is not easy. It involves many, many steps. And there are various types of steps. So you have additive steps. You're adding, let's say, dopants to change it for the semiconducting to conducting behavior. You have etching, removing materials, of course, all the masks and so forth. And then you have transformative steps, where you're transforming, let's say, silicon to silicon dioxide. All of these are very complicated things that are done in class 0 clean room and so forth. So we were not doing anything as fancy as that. But of course, we still have a 3-terminal device. So these are 3 electrodes. The way that we were doing it was to basically write a T-junction, and that's where, in the middle, where our transistor is going to be. We start with wide wires that are maybe 12 nanometers wide, and then we erase a 1 micron area to do our writing so these are like our electrodes, virtual electrodes, and then we write a T-junction out of 2 nanometer wide wires. Now, at any given moment, we can always measure what's going on. And at this point, it's really boring because it's basically just a resistive network. So you have a straight line. If you have source and drain and gate, basically everything is kind of boring. And then the last step is basically to create that barrier here and to move this gate a little bit back. And that's what we're calling a sketch set. And basically, it works very much like an ordinary transistor. When you apply a positive voltage here, then electrons can flow between source and drain. That's the blue curve, so it's in the highly conductive phase. And then as you make the gate voltage lower and lower, you start to see that now basically current is blocked at low voltages. So it basically can turn the switch on and off at very small scales. Okay, so how could this possibly be relevant for real technology? Well, that's a good question. It's something that we've been thinking about. But I want to, again, point out or contrast the existing ways in which transistors and memory are made nowadays. They're made in huge facilities, right? This is Fab 32, Intel's facility in Chandler, Arizona, 17 football fields. Right? So what we're interested in doing is shrinking what is needed to make nanotechnology, to make something that can compute and store information by maybe 10 orders of magnitude. Right? So the idea is to be able to make something that can in fact produce circuitry, useful circuitry, in something that you can hold, a size that you can hold in your hand. Now, there are many reasons why you might want to do that, but it's definitely a different way of thinking about this. The other thing I want to point out is that, of course, there is this issue of convergence, that there's a price to pay for making logic and memory out of different materials. It's just very hard to integrate them. And there's the richness of this physical material system may allow for some convergence to take place. Again, I'll also allude to a project that was led by IBM, the so-called Millipede project, which was, it's actually, they're not so active in it right now, but the idea was to have thousands and thousands of cantilevers. So this would be a way of scaling up from one probe to thousands, and this was, of course, for storage only. And the challenge was to basically take one of those atomic force microscopes and then multiply it by 1,000. Well, they were successful. They actually made 4,096 of them on a very small, pinky-size data sled. But then the real challenge was finding the appropriate medium. So now, actually, I've been working with a professor at Northwestern, Chad Merkin, who is working on the Megapede, which basically they've already demonstrated over 10 million cantilevers, so not cantilevers, actually sharp probes on a surface that can be scanned and be used to do probe-based storage, manipulation, and so forth. So I think there's some promise here in terms of being able to scale up parallelize this writing process. Okay, so the last part of this is future directions. And this is where I want to talk a little bit about quantum mechanics and quantum information, because I really think I agree with what Barbara was saying, is that if you're working with quantum mechanics, you do have this ability to override Landauer's criterion, which is that the irreversible computation necessarily produces heat dissipation. But also, there are many advantages of using quantum mechanics over classical mechanics to do computation. And so the idea is that you take two quantum mechanical states of the universe, you call one of them 1 and you call one of them 0, and we know that from quantum mechanics linearity that we can take a quantum superposition of those two states. And the question is whether you can do anything useful with that in terms of computation. Well, Peter Shor showed that you could do that. But basically, again, information is physical, but so is quantum information. And this is an alumnus of IBM, David DiVincenzo, who was writing about some of the history of quantum information at IBM and other places. One of the very popular systems that people have been looking at, maybe because of its textbook simplicity, is the spin of an electron. So we know that spin 1/2 has two possible states. You can call them up and down. And those map very neatly onto the 0 and 1 state that I was referring to before. So quantum information is stored in physical systems just like information is stored in physical systems.